Okay, so this is the week 3 assignment problems we are going to solve right now. So let us begin. So question number 1 is the commutator of two Hermitian operators is a Hermitian. We have to find out whether that statement is true or false, right? So first of all, you probably already know what it means to be a Hermitian operator. So Hermitian basically means that if you have an operator A, so this hat sign means this is an operator. So this A operator will be Hermitian if A equal to A dagger. So I think you are also familiar with this dagger sign. This is the like Hermitian adjoint sign that we call, that we identify by dagger. It basically means you take the transpose conjugate of that operator, which is basically written by a matrix. You probably know that operators are mainly written by mathematically written or expressed as matrices, just like um, we know that that is a mathematical expression. So let's say if you have a operator given by a1 a2 a3 a4, so this is a 2 cross 2 matrix, let's say, just for example. And a1 a2 a3 a4, all these numbers can be complex numbers, right? They are not necessarily to be real. Then its dagger matrix would be uh, transpose conjugate of that. So first of all, taking a transpose of a matrix means you change the row to column and column to row. So basically a1 a3 goes as row now, which were previously as column, and a2 a4 goes as the other row. Now the transpose has been done and has been taken. Now take the conjugate, complex conjugate. So assuming that all these are complex numbers, so all of them will have a complex conjugation sign right now. And this is how we take mathematically the dagger or the Hermitian conjugate of that operator. And when do you call, when this relation is satisfied? So this is not a necessary condition to be satisfied, but if this is satisfied, then we call this is a Hermitian operator, right? So this is the definition of a Hermitian operator. Now the commutator of two Hermitian is a Hermitian. You have to prove that. So let us, for this kind of problems, always, because they are saying that commutator of two Hermitian operators. So let us choose our operators as A and B. Let's say they are two Hermitian operators that we have taken or you have assumed. So they are Hermitian means necessarily they satisfy this condition, a cap dagger equal to a cap and b cap dagger equal to b cap, because they are given to be Hermitian. Now you have to see whether their commutator behaves as a Hermitian or non-Hermitian. So commutator means you put these two operators in a commutator bracket, which is this bracket, and you know the formula of commutator bracket. So this a and b commutator relation is ab minus ba. So because they are operators, don't confuse them as simple products of a and b, but this ordering actually matters, that a b product and b a product, this operator, these sequences are not the same. So because they are operators, remember. So a b commutator bracket equal to a cap b cap minus b cap a cap, right? And whether now how to see whether that is a this thing. Let's say this is a new operator. Let's say this operator is called as what do you call it? So let's say this is your R operator. So this new operator is nothing but a self commutator operator of A and B. So this is A cap B cap minus B cap A cap, and if R cap dagger equal to R cap, then this commutator bracket operator is Hermitian. So we have to see whether that is satisfied. So what is R cap dagger? This is basically A cap B cap commutator bracket whole dagger. That means this is product of A cap B cap minus B cap A cap whole dagger. Now you also know this means that individual terms will have a dagger sign right now. AB whole dagger minus BA whole dagger. Now you also should be familiar with this formula, that if AB whole dagger is there, that is expressed by B dagger times A dagger. Similarly, this BA whole dagger will be expressed by A dagger B dagger. Now you know individual operators are already Hermitian, so B dagger means B actually, and A dagger means A because they are Hermitian individually. And A dagger is again A and B dagger is B. So what you get is minus of A cap B cap minus B cap A cap, which is, you remember that this is the AB commutator bracket relation. That means it is minus of A cap B cap commutator bracket. So basically what you get is that AB dagger commutator brackets dagger is equal to minus of AB commutator bracket. That means it is not Hermitian because we are getting that R cap dagger, which is this one, equal to minus of R cap, and this kind of relation is called skew Hermitian because it is not equal but there is a negative sign there, so that is why it is called skew Hermitian. If it was with a positive sign, just simple R cap dagger equal to R cap, then we could have said that this is Hermitian, but in this case this is skew Hermitian and not Hermitian. So the statement in the question is false. That is our answer, that this statement will be false. This is the accepted answer as well. Now question number 2 is, which of the following operators are Hermitian? Again there are 4 options given and you have to prove whether, you have to check whether this operator is satisfying this relation, then it would be Hermitian, and if not then it will be not be Hermitian. So now here out of 4 options you don't have to solve all of them because you can see this one d by dx, this is a derivative operator with respect to x, and I d by dx is almost similar except for the I factor given there. So once you get this ddx's relation to be Hermitian or not, you can easily like find out what will be I ddx behavior. And similarly, if you know ddx, you can easily predict e to the power d by dx Hermitian or non-Hermitian. Similarly, this is known, then easily e to the power that factor will be known, because exponential factor does not add anything to for the operator being Hermitian or not, right? Because Hermitian is all about taking transpose conjugate. So whether the matrix elements are exponential, it does not add to its complex conjugacy or to the transpose. So that is why once you know this and this, you can easily predict this and this just based on the similar behavior, right? So this is the problem made simpler. Now we have to first find out whether d by dx is Hermitian or not. So for that, again let us take this page and let's say in this case our A operator is d by dx, which is our option number A given. Now to check whether A dagger is A or not. So whenever you have a quantity operator representation given like this, so the best case scenario will be to identify the behavior of an operator will be apply the operator on a wave function or a state, and that is also not enough. You have to, it is better to take the expectation value of the operator because that is the physically identifiable or physically measurable quantity that an operator can give. Basically an operator is an observable, so observable means that it measures a quantity. So it will only be physically meaningful when you take a expectation value or sort of an average for that operator acting over a state. So that we'll be doing here. So expectation of any operator taken for it acting upon a state is a physically measurable and meaningful quantity. So that is what we'll be checking here, right? So yeah, so basically A cap expectation value means if you have a state as psi, then this is given like this. This is the expectation value of the operator A. Psi is a state, any random state, that is. So this means that you have already seen how the expectation value is expressed. So this is psi star x a cap acting on psi x dx, whether x's limit is from minus infinity to plus infinity. Now because psi x is a general state, but you know the expression of a cap, so that we put here, that is acting upon psi x dx. Now you can solve this integral by parts. So first part remains as it is. Now ddx of psi x, when you take an integral over it in the by parts term, the first term will be integral over this, so it will be simply psi x, and the integral limit will be taken from um, sorry the integral limit will be taken from minus infinity to plus infinity on this psi x, minus the second term of integral by parts will be, this first term will have a d dx dot derivative, and the second term will be under integral, so it will be again psi x, then dx, and then the final main integral, and then x going from minus to plus infinity. So now you know that any real wave function representing a physical state will go to 0 as the x goes to plus minus infinity. For a physically meaningful state or a physical state, it is always true that as x goes to plus minus infinity, the wave function for that physical state should go to 0, right? So by that relation, this will go to 0, and you get only this term is remaining, which is this. Now this is, here you can see there is a ddx term now, right now on the first term. Earlier it was on the psi x term, right? So then you can, there is also minus sign outside the bracket, so it can be written like this, that this is minus 2 plus infinity ddx of psi whole star psi x dx. Now this can be taken star outside, because x is the position, it cannot be complex, it's real, position is real, x can't be, position can't be complex. So whether you take ddx or ddx star, it basically means the same, right? So ddx star is nothing but ddx so let me write it again. So ddx star is basically nothing but ddx, because position derivative, so position cannot be anything but real, so star sign does not change anything. So by that you can write this ddx d psi star dx as a whole bracket with star as d psi dx of star. Now the purpose of writing it like this is that now we can write this is ddx of psi and psi in this bracket, or because ddx is nothing but this operator a cap, so this is a cap psi and psi like this. And you know that whenever there is a in the bracket notation there is something in a kate form like this a cap psi, you can convert, you can take the a to the other side by taking a dagger sign on a, or taking the Hermitian adjoint factor. So this is a cap dagger, it has now becomes a cap dagger, and the psi kate has come separately. Similar thing can be done here, that a cap psi is replaced by this expression, so this means psi a cap dagger psi, right? So you get minus psi a cap dagger psi, which is, if you now describe this a cap dagger as a new operator, so this is taken with a sandwich between the two wave function psi, so this is basically the expectation value of a cap dagger operator, and there is an extra negative sign outside, so this is basically expectation value of a cap dagger. Now remember what you started with, you started with a cap expectation value, right? So on the left hand side you had expectation value of a cap, on the right hand side you are getting expectation value of a cap dagger with a minus sign. That means you are getting a skew Hermitian operator as ddx equal to a cap, because for a Hermitian thing this minus sign should not be there, directly this should be equal to this. So this is a skew Hermitian, that means option A is not Hermitian. Now option B was, now your a cap is defined as I times d dx. So whenever there is a I, you can say, you can clearly predict that whether what this I will affect on the, how this I will affect on the relation earlier that is described for d dx. So this is very simple, still you can still calculate it and derive it on your own, but you will finally find out that because there is a I sign here and I is a complex number where I star equal to minus I. Earlier what you did is that d dx is entirely real, so d dx star is equal to just d dx. Now from this relation, you have a I d dx, right? So basically again, if you take, let's say on the LHS you have a expectation value and you have minus to plus infinity psi star I d psi dx. Now this I comes outside, and by solving the integral you again get psi star psi from plus to minus infinity, which goes to 0, minus of, again minus to plus infinity d psi star dx psi dx. Now this thing with the extra I is there, which was not earlier, which is not there earlier. So this is minus infinity to plus infinity I d dx of psi star psi dx, right? So now we can express this as I d dx of psi whole complex conjugate star psi dx. Why this is true? Because I d dx psi whole star is minus I. Now I becomes minus I because of this complex conjugation sign, and d dx is real, so it becomes d dx under, remains d dx under star sign, and psi can be complex, so psi becomes psi star. So this is same as this thing with a negative sign taken inside. So this is how we can express this thing on the alternate terms. So ultimately it tells you that this is minus to plus infinity, this is our operator, main operator a cap psi whole star psi dx, which is nothing but the, in the bracket notation, this is a cap psi expectation value. And as I said earlier, that this can be written as psi a cap dagger psi. So basically you have now psi a cap dagger psi. This is the expectation value of a cap dagger. So you started with a cap, where a cap is I d dx. Expectation value of a cap is derived as expectation value of a cap dagger. That means it is true to be Hermitian. So d dx is Q Hermitian, but I d dx is Hermitian. So option B Hermitian. Now option C was e to the power d dx operator, if that is a cap, then it is Hermitian or not. Basically, as I said, exponential factor does not change the mathematical derivation in any way. So if d dx is not Hermitian, then e to the power d dx is also not Hermitian. Similarly, option D was e to the power of I d dx equal to a cap, and because you also already derived that I d dx, this operator, is Hermitian, that is true, then e to the power I dx is also Hermitian. That means you are getting B and D are the only two options that are Hermitian, and A or C as Q Hermitian. So our answer will be which of the following operators are Hermitian is B and D. B and D. This is also the correct answer. Now option 3, question 3 is, consider two operators A and B defined by A psi x equal to psi x plus x and B psi x equal to d psi dx plus 2 psi x. Which of the following statements about the linearity is true? So linearity of an operator is expressed by a certain relation that I am going to write here. So let us write side by side here, because I have to see this expression of A and B for me to solve it. So an operator O cap is linear if the general condition is satisfied that O cap operating on C1 F1x plus C2 f2x, where c1 f1 plus c2 f2x is a general state psi x that is given in general. c1 c2 are constant coefficients that can be complex as well, and f1x and f2x is just function of x, and their combination is expressed as the total wave function psi x. Then linearity, if that is satisfied, then that means that right hand side will be equal to, so if this is LHS, then this will be equal to RHS equal to c1 as a constant comes outside, and the operator acts on the first x dependent term of the wave function, then plus sign is separated, and then again c2 separated, and the operator acting on the second x dependent term of the wave function. So if this satisfied, then we can say that this operator is linear. So in our case, if A and B have to be checked as linear or not, then simply, because there is an expression given of A psi x equal to psi x plus x, then let us say we have to check whether for this case of this expression of A, this thing is satisfied, LHS equal to RHS is true or not. Then let us take the LHS first. LHS is simply O cap replaced by A cap, C1 f1x plus C2 to x equal to, so A cap acting on this thing means this whole thing is basically your psi x, and the expression is psi x plus x. So that means this is c1 f1x plus c2 f2x plus x, and RHS will be equal to, this thing is your RHS, so c1 A cap acting on f1x plus c2 A cap acting on f2x. So c1 A cap acting on psi x plus x is f1x plus x plus c2 acting on f2x plus x. So it is basically c1 f1x plus c2 f2x plus c1 plus c2 times x. So you can clearly see that LHS is not equal to RHS. That means A cap operator with this expression of A, this definition of A, is not a linear operator. Now for checking for B is B equal to d psi dx plus psi 2 psi x. So for B, B psi x equal to d psi dx plus 2 psi x. Now to check linearity, again LHS is equal to B acting on C1 f1x plus C2 f2x equal to, this whole thing is the psi x now. So B acting on psi x is d psi dx, that means d dx of C1 f1x plus C2 f2x plus 2 of C1 f1x plus C2 f2x. Now because derivative acts on each of the terms separately, and C1 is a constant, so it is x independent, so it is C1, let's say derivative of f1 is f1 prime x, and derivative of f2 is represented by f2 prime x plus 2 of C1 f1x plus C2 2x. Similarly, RHS is B cap acting on C1 B cap acting on f1x plus C2 B cap acting on f2x. That means C1 d for f dx is d for dx is f1 prime x plus 2 f1x plus C2 times f2 prime x plus 2 to x, which is C1 f1 prime x plus C2 f2 prime x plus 2 C1 f1x plus C2 if 2x. Now you can compare and check that these two are exactly same. That means for definition of B operator, LHS equal to RHS. Hence, B cap operator is a linear operator. But earlier we got that A cap operator is not a linear operator. So your answer option should be chosen as um, B is linear but A is not linear. That is correct answer is B. Okay. Question number 4 is, which of the following statements about projection operators are true? So projection operator you have to first know and understand, and then its properties. From if you explore its properties, and out of the four options which ones are true you have to find out. So the first option is it has to be a Hermitian and it's equal to its own square. So if you have already learned something about projection operators, then it is one of its most obvious and most critical properties that projection operator is its own square. That means if P is a projection operator, then it has to be satisfied that P cap dagger is equal to P cap, that is its Hermitian, and P square equal to P, that means it is equal to its own square, which is also known as idempotent. So whenever an operator behaves like this, it's called an idempotent operator. And P projection operator is generally defined by this, that this is phi I, let's say bra, and phi I ket. So this is like this kind of a bracket relation projection operators are given as. Now, so if that is true, then this is a must satisfiable condition that phi I is basically orthonormal eigenstates or orthonormal basis states phi I. That means they must be normalized, because orthonormal basis states has to be normalized to represent any physical meaning. So the second option is already true. You can say that it is a projection operator only if psi is normalized. So see here projection operator psi is basically the general relation of phi I here. So if we are saying that phi I orthonormal basis vectors, that means psi in this expression of a projection operator has to be normalized. So that is already true. Now the other so the first one is also true, so you can prove it. I can show it to you that it is definitely true. And the third one is projection operator are said to be orthogonal if their product is 0. This is also true. I can show that. And the last one is the product of two projection operators is also a projection operator. This is false, because this is only true if the projection operators, the two projection operators that is being discussed about, are commutating with each other. So only true if the two operators P1 and P2 commute with each other. Otherwise, this is not true. Right? So let us derive and solve each of the statement one by one, why we are choosing that to be correct. So this is question number 4, and this is about projection operator. We define it as P is equal to where phi I are orthonormal basis vectors. So instead of phi I phi, one can also identify it as psi like given in the question. Can also where the condition is that psi has to be normalized wave function. So then the first property is it has to be Hermitian. That means P dagger equal to P. So basically to prove that, we can operate this P on a B state. That means this is psi acting on B, and psi B, this is basically a number, not a state anymore, because this is the sandwich or bracket product of two states. That means it's a number. So we can take the number as a like non-state value, so you can take it anywhere you want, like a constant term, and the psi is a state, so it comes on the right. That means this is giving us this. Now if you operate a ket state on the left side, then this whole thing is a ket acting on the P acting on B state, right? So this is basically A psi B psi. Now basically because this is the constant, so psi B comes on to the other side, and this is this, right? Both are numbers. Now this means that you have A P B equal to this. Now what happens if you take A if you take P A and then sandwich it with B bra vector. So this PA is basically A PA is basically, you write down the expression of P. This is psi and A. This is on kate vector and then B. So kate means this is a complex conjugate. So psi A, even if it is a number, it can be complex. So the complex conjugate is taken outside, and this psi kate will be psi star, right? So that means psi kate will be psi star. That means this is psi but psi is already star, means is taken in kate, so this is psi B. Now because this thing is a complex conjugate, so you can express psi A star as A psi. So this is nothing but the same expression. That means you are getting that A P B is equal to P A B. This can be written as, you can see, have seen from earlier, this can be written as A P dagger B. That means you get in the LHS A P B equal to A or B. A and B are two states, any two states. Then this is equal to A P dagger B, or you get A equal to P equal to P dagger, because the expectation, or the like sort of expectation value, you can say that between two states is giving you the same for P dagger. That means it is a Hermitian. That is proved. Now to prove whether P square equal to P, now P squared equal to P or not, for that we again apply it on some state, right? So this is, let's say, on B. So P on B, see psi so this becomes basically psi, and this thing becomes actually psi this thing, and psi B. So this is a number psi bracket is basically mod psi whole square, which is equal to 1, because psi has to be normalized. The remaining terms are, this is 1, so this is a number, so this is just psi B psi, which is, if you simply act P on B, that also gives you the same thing, because this is psi bra psi kate on B, which is nothing but psi B number and psi. So this and this are same, hence P square equal to P, this is square of its own equal to square of its own square, so this is also true. So the option A is correct, option B is correct, we have already found out. Now what about option C, that the product of the two projection operators, what did it say? The product of two projection operators um, um, is 0 if they are said to be orthogonal. That means uh, if two projection operators P1, P2 are orthogonal, that means when they operate on any two states u and v, this thing P1u, P2v, this will be equal to 0 if they are orthogonal where u and v are any state, right? So let us see what it gives you, that P1u, P2v, expectation value is basically u, P1 dagger, P2 v. This is your LHS equal to, now so this is basically because you know that P1u, when you take this in the inside the kit and take the want to take P1 outside the kit, then you take it out as P1 dagger to the other side, right? And you know that because they are individually projection operators, so P1 dagger equal to P1 and P2 dagger is equal to P2. So this is basically u, P1, P2, v, right? So this is only 0 if P1, P2 is 0. That means their product is 0. So it's true that for these two operators to be orthogonal, their product has to be 0. So this is option C is also correct. Now option D was incorrect. It said that two projection operator product has to be a projection operator. That is not true. So let's see that if the product of two projection operator is P, that means P equal to P1, P2. It's the product. So each of P1 and P2 are projection operators. So P1 dagger equal to P1 and P1 square equal to P1. So they are satisfied. They are satisfying projection operator properties. Similarly, P2 dagger is equal to P2 and P2 square equal to P2. So if P equal to P1, P2, then what happens to P? Whether its P satisfies P dagger equal to P and P squared equal to P, then only you can say that this is a projection operator. So let us start with this, P square equal to P or not. So basically P squared becomes, so P square acting on U and V equal to U, P1, P2, V. So this is basically P1, P2 whole squared. Now U, P1, P2 whole squared, so again P1, P2, V. Now if P1 and P2 commute, that means P1, P2 commutator bracket is 0. Then P1, P2 minus P2, P1 equal to 0. Then P1, P2 would have be same as P2, P1. They commute. So if this is true, that means you can combine P2, P1 as P1, P2, right? And you can simplify the rest of the terms very simply because now two P1s are together. So this is P1 square, two P2s are together. So P2 square V. And you know that P1 square and P2 square are individually equal to P1 and P2 square equal to P2 because they are independently projection operators. So that is P1 and P2 V. So that means P1's, this is basically nothing but U, P, V. So P squared equal to P satisfied only if P1, P2 commute or this relation is true, otherwise they cannot satisfy this. So the answer will be wrong, that option D is not always correct. So option A, B and C are the correct answer. So D is wrong. A, B and C are the correct answers. Question 5. Consider a ket psi equal to something is not normalized. It can be normalized by multiplying it with a factor of 1 by root over a. What is the value of a? So this is a very simple question. You have to normalize psi and find out what is the factor missing for the normalization to be equal to 1, because that is the condition for normalization, that psi whole mod square should be equal to 1. Now here the catch is psi is written in a bracket notation, where psi bra is equal to phi by 2 minus I, a matrix like form, as I said, so not matrix, but it's a wave function vector. So this is, let's say, see again, phi by 2 minus I. Question number 5. Psi equal to phi by 2 minus I. Now to be psi to be normalized, this condition has to be satisfied, that psi bracket is equal to psi whole mod square equal to 1. Now this is equal to psi ket psi bra, so that means psi bra is already this. So then psi ket will be, as I said, this will be transpose conjugate. So transpose means row going to column. So this is phi by 2 minus I and the complex conjugate outside. So this makes it minus phi by 2 plus I. This is phi by 2 minus I. This is equal to 1. So that means this is, if you multiply this to this, minus 25 I squared plus 2 into 2, 4, minus I squared equal to 1. So 4 minus 26 I squared equal to 1, minus I squared is plus 1. So basically 4 plus 26. So this is not equal to 1, clearly you can see. So normalization condition is not satisfied because this product is coming as 30. But it has to be 1 for psi to be normalized. So how to get it to be 1? So just multiply this by a normalization factor a. Okay. So a is, let's say, your normalization factor, and take the value of it as 1 by root over 30. Then with each of, because a is a constant, there is also a on this term. So whenever you take psi ket psi bra, there is a coming from here and a coming from here. So this is multiplied by a squared, which is a squared, and this is basically a squared is 1 by root over 30 whole square into 30, which is nothing but 1. Now it is normalized. So for making it normalized, you have to take a constant multiplication factor a equal to 1 by root over 30. So let us choose our answer, that for it to be normalized, the a value will be 1 by root over 30. Sorry, in this case it was multiplied by 1 by root over a. So what answer you got is 1 by root over 30. That means here a equal to 30. Right? So this is the correct answer. Now question 6 is, consider a ket like this, minus 1 plus I, 3, 2 plus 3I, and bra like this. Value of psi ket phi bra will be a minus bi. So basically it is nothing but a bracket notation practice problem. You have to very carefully take the terms and just multiply it by choosing the correct bracket notation, and you will get the answer easily. So let us do that. Psi phi, here psi is in a ket notation and phi is in a bra notation. So in the question, psi is given in the bra notation, so you have to change it to a ket notation. That means you have to take this thing, complex conjugate transpose, that means minus 1 plus 3i, 3, 2 plus 3i, transpose, and then complex conjugate. So what it gives you, first transpose, make it to row, 2 plus 3i, and then the complex conjugation sign changes this sign as well, minus 1 minus I, 2 minus 3i. Similarly, phi is given in the ket notation, but phi for the bra notation is basically the complex transpose conjugate of this. So this is basically 6 minus I, 5 transpose conjugate, which is nothing but row going to column, 6 and then also becoming complex conjugate. So these are real, nothing changes by the star, but I is complex, so it becomes minus to plus I, and then 5. Now once you have got this and this, now just carefully multiply that. This is first shy get, that means minus 1 minus I, 3, 2 minus 3I multiplied by 6I, 5. So this is multiply minus 6 minus 6I plus 3I plus 10 minus 15I. This is equal to plus 10 minus 6 is plus 4. 15 and 6 is 21. 21 minus 21 plus 3 is minus 89. So 4 minus 89, that means your A is 4 and B is 18. So A is 4, B is 18. This is our correct answer, matched. Now question number 7 is Hermitian adjoint of f of A is what? So basically linear operator A is not equal to A dagger, then you have to find out what is f of A, this operator's Hermitian adjoint. That means what is f of A whole dagger, right? So let us write this expression very carefully. Let us choose this page only because I'll forget this expression. So you can take a fresh page on your copy and solve this with me. F of A whole dagger, you have to find out. This is the Hermitian adjoint definition. So f of A is minus 1 minus 2IA plus 3A multiplied 1 plus IA minus 2A. This whole product's whole dagger. Basically A into B whole dagger is B dagger A dagger. So that same thing happens. This term comes at first. So 1 plus IA minus 2A dagger multiplied with as a product 1 minus 2IA plus 3A dagger. So this is dagger means transpose conjugate, right? So this becomes 1, or let us not go into that because they are only asking for the expression. So B dagger A dagger is basically this. So if you take dagger on this, so it becomes 1 minus I A dagger minus 2 because this is real A dagger. The second term is 1 plus 2I A dagger plus 3 A dagger. So let us choose what is the correct answer. 1 plus I A, 1 minus I A dagger minus 2 A dagger, and 1 plus 2I A dagger plus 3 A dagger. So this is the correct answer. Now you might like think that why this thing has not become anything else. This is just a linear relation, right? It has only plus and minus sign. I was initially confusing with the signs to be different. This is not some row or column expression. This is a single form, single line. So here only the terms which matter under the dagger sign, like the A, has been changed to A dagger, and also the complex conjugate relations applicable, that's I to minus I, like that. Other real terms remain as it is, and you have got your answer correctly as B. Now evaluate the commutator XH, double commutator where H is the Hamiltonian operator. Now this thing we need a different page. So this is question number 8. Now if nothing is mentioned, then generally by Hamiltonian you only assume that this is a kinetic energy term contributing. No potential energy term is specified, so you really don't know what potential to take, so don't go into that because generally it is the potential energy plus kinetic energy. But if nothing is specified, then just ignore this and only focus on the kinetic energy term which is known to you in the form, that is p squared by twice m. So in 3D case it is not just p square but px square plus py square plus pz square, all three directions. Now your commutator bracket is asking x comma h. So first let us take x and h, which is basically x 1 by 2m px squared plus py squared plus pz squared. So by canonical relation you already know that x with px is giving you ih. This is some standard relations. I hope I do not need to re-establish this forms. These are standard, already solved in the previous assignments and discussed in the lectures as well. So x px equal to ih cut, similarly y py equal to ih cut, and similarly z pz. But other than that, the other variables like x py would give you 0, or x pz will also give you 0. Only x px is giving you ih cut. Similarly, what is px x? It will be simply minus ih cut, and the pyx will be also 0, just, and pzx will also be 0. Another thing is, if you have a commutator bracket like this, that this is, sorry, there is a b c, then there is a product of b and c. So first you take a and b, then c, or you take b, a and c. So this sequence matters, right? So this is something that we need to use here for simplifying. So here 1 by 2m term counts outside because it's a constant. So then x, now each of the terms will be taken separated in the plus signs inside, because that is a sort of a linear thing to do, right? Now very naturally x py square will go to 0 because they are different variables, and x pz square will also go to 0 without thinking much. So only relevant term is this. Now this means x px times px. So this is similar to this kind of relation, only that b and c are equal in this case, but the relation remains same. So this is x px and px outside plus px times x px commutator bracket. And now this is very simple because you know that x px is I h cut. So do not use randomly the third bracket anywhere in this case, because third bracket in quantum mechanics means commutator bracket relation. So use second bracket instead. So this is I h cut px operator plus px operator times I h cut, and I h cut is a constant, so it takes outside. It is taken outside. I h cut by twice m 2px, which is I h cut by m px cap. Now once we have got that, now the final expression to be obtained was x, another commutator bracket. So we have just arrived at this. So we replace this in this relation, I cut by m px cap. Now this is pretty simple because I h cut by m comes out, and this is simply x px commutator bracket, which is known to be I h cut. So this is I squared h cut squared by m. This is minus of h cut squared by m. So let us choose our answer. This is the correct answer. Now question number 9. Consider the states psi equal to this thing and chi equal to another thing, where phi1 and phi2 are orthonormal vectors. That means they are orthogonal to each other and they are normalized within themselves. So orthonormal definition is also very important in quantum mechanics. Phi1 and phi2 means they are orthogonal within themselves. That means phi1 phi2 product like this will be 0, but they are normalized within themselves, like within individually themselves, like phi1 phi1 sorry, not 0 1, and phi2 equal to 1. Similarly phi2 phi1 will also be 0, right? So this is the condition for orthonormal vectors, and with this relation you have to identify, find out what is, let us solve it here only. Psi plus chi, psi plus chi. So basically psi plus chi, this new vector you have to first find out and then take the normalization like this. So first psi plus chi, this will be simply psi vector, psi kit, psi bra plus chi bra. So psi equal to 3i phi 1 minus 7i phi 2 minus chi bra equal to phi 1 phi 2. So this is 3i minus 1 phi 1 minus pi by pi 2. So from this psi plus chi, kth notation will be simply transpose conjugate of this. So by conjugate, this 3i minus 1 becomes minus 3i minus 1 and phi 1 becomes from bra to kth, and this phi y becomes minus phi by 2 plus phi y and phi 2 bra to kth. Now assembling the terms, psi plus chi, psi plus chi equal to minus 3i minus 1 phi 1 plus phi y phi 2 3i minus 1 phi 1 minus phi y phi 2. So because you already know that the cross terms will give you 0, that means phi 1 to phi 2 will give you 0, so no meaning, and phi 2 to phi 1 is also 0, no meaning, because they are orthonormal, means orthogonal plus normalized. Only the relevant terms are these terms, that is phi 1 to phi 1, that gives you non-zero and 1, and sorry, phi 2 to phi 2, non-zero and 1. That means you get, by this product, you get minus 3i minus 1 plus 3i minus 1, this product into 1, plus phi y into minus phi y into 1. So this is basically this is, if this is z, then this is z star, right? The complex conjugate of that. And if this is z, this is z star. So let's say z1 z1 z2 z2. That means mod of z2 squared. So this is root over of 3 squared plus 1 squared whole squared plus that means this is 10 root over of 10 whole squared plus this is root over of 25 whole squared. So this is basically 10 plus 25, that means 35. Let us check whether we have done it correctly or not. Yes, the answer is correct. It is 35. Now question number 10, final question. Consider the state, again a similar question. Psi 1 equal to phi 1, phi 2, phi 3, phi 4, linear combination of them. So just like the earlier question, only instead of 2 there are 4 phi's, and phi 2 is again phi 1, phi 2, phi 3, phi 4. They are orthonormal kets and A is constant. So the value of A find out so that psi 1 and psi 2 are orthogonal. Now the condition given by them is that you have to satisfy the relation such that this A is the unknown constant value is derived such that psi 1 and psi 2 are orthogonal. That means psi 1 psi 2 bracket equal to 0 if orthogonal. So let us solve it here. So if this is 0, then it is orthogonal. So to satisfy that, let us choose the terms very carefully. So psi 1 ket is given, psi 1 bra is given, you have to take the psi 1 ket. That means it will be minus 2i phi 1 ket plus A we don't know, so we take A star. A is not mentioned to be real anywhere, so we assume it is complex. So A star phi 2 sorry, not phi 2 was not a with a, this is a star phi 3 kit plus 2 is real, so nothing changes, phi 4 kit multiplied by 2, so it remains same because phi 2 is remained as bra not kit, so no change needed. Right, so again these are orthonormal basis, that means phi 1, phi 2, phi 3, phi 4, they are all orthogonal with respect to each other and are normalized within themselves. That means no cross terms will be allowed, no cross terms will be valid because all of them will give you 0, because this relation will be same true, phi 1 phi 2 equal to 0, phi 2 phi 3 equal to 0, phi 1 phi 3 equal to 0. Similarly phi 2 phi 4, all combinations possible as 0 if they are not same, and if they are same then phi I equal to 1 for I equal to 1 2 3 4, within themselves they are normalized. That means only you have to look for similar terms. So this phi 1 kate and phi 1 bra giving you minus 4i, then this and this giving you minus 3i plus 3a star minus 2. This is 3a star minus 2 minus 7i. To be orthogonal, this is equal to 0. A star equal to 2 plus 7i by 3. So the correct answer is, sorry, there is a sign mistake. This is not plus 7i, this is minus 7i you got. So minus 7i plus 2 by 3 is our correct answer, which is B. So thus we have solved all the questions correctly. These 10 questions are for this week's assignment. So